transitions, the electronic transitions, unit 2, electronic transitions. So this when we refer to the molecule as being excited to higher electronic level, we indicate that an electron has been moved from higher energy to another, say this is lower energy to higher energy. So this is lower energy to higher energy. Another. This electron cloud, be any of the type we have already encountered, including sigma 2 pi electron. Only the fairly loosely held n and pi electrons in the UV spectrum are permitted to be excited. When valence electrons observe light, whether visible or ultraviolet, the usual states of these electrons are excited to the more energetic levels. In electronic transition, the orbitals energies have fixed values. Energy has been quantized, electrons are promoted from lower energy bonding orbital to higher energy anti-bonding orbital. Foreign types of transitions originates as a result of absorption of compound. Absorption by compound. Sigma to sigma star, n to sigma star, pi to sigma star, and n to pi star, very important. So these are the types: sigma to sigma star, n to sigma star, pi to pi star, n to pi star. Say first sigma to sigma star happens in the molecule CH3. So only see you observe CH3 molecule or CH4 molecule, actually this is not CH3, CH4 molecule. So CH4 or any CH compound, only sigma stars, only sigma star electrons. In the N2 sigma star, it should contain one lone pair of electrons. N means lone pair. So sigma star antibonding. Pi to pi star antibonding at least contains one double bond. N to pi star at least it contains one lone pair and one double bond. So first the sigma to sigma star. So these are the energy. So this is sigma, this is pi, this is n, and this is pi star, this is sigma star. So this is bonding and this is anti-bonding, sigma star. Pi is bonding, next anti-bonding. Another middle one, neutral, that is non-bonded. Now if it is sigma to sigma star, sigma to sigma transition occurs in the CH bond. These are in the form of which types of bond? CH2 bond. See, already I told, so the absorbance maximum is 200 to 700 nanometer. Here is 200 to 700 nanometer. Okay, belonging to the UV belonging to 200 to 700 millimeter. But sigma to sigma transition, first transition, it requires very high energy, that is maximum 125 nanometers. That's why it is not belonging to that way is not allowed transition. Sigma to sigma star is 125 nanometers, but it requires 200 to 700 nanometers. In N to sigma star comes this N to sigma star. This belongs to this one. This second type after sigma to N to sigma star. This is this one. This M to sigma star. N to sigma transition. This over. This transition over sigma to sigma star. Now N to sigma star. So N to sigma star transition. This also belongs around 150 to 250. This is also forbidden. So this it should contain lone pair and one sigma bond is the condition for this transition. One lone pair. Compound should contain at least one lone pair and one sigma bond. In this compound, pi to pi star, this transition occurs in the compound containing conjugated system. The bond horizons, enons, TTC. So this is also called K bands, also appear in the aromatic compound. The transition is called K bands. Compounds like dienes, polyenes, see this is dienes, polyenes, K bands also appear in the aromatic compound, substituted by a chromophore. if this conjugated system is in the butadiene, in the aromatic system, one chromophore is attached, then the intensity is enhanced. The intensity of K band is usually more than 10 to the power of 4. See this, how much is that? The K band absorption due to conjugated enes. Enones are affected differently by changing the polarity of the solvent. So in the fourth type, N2 pi star, so this is low energy and high energy. So hence it is quite easy to tell whether the transition N2 pi star or pi to pi star. How we have to stay? So this is occurring, the pi to pi star occurring around 290 and 180 respectively, absorption occurring at low wavelength is usually intense. Hence it is quite easy to tell the transition is N to pi star or pi to pi star. You need to distinguish this type of transition by analyzing aldehydes occurring 290, this second one occurring 180. Pi to pi star usually pi to pi is occurring around 290, but N to pi star 180. Okay, N to pi star 180. So that's why 290 is pi to pi star, N pi star is 180, N to pi star is 180. So N pi star and pi star, because of the excitation coefficient for the former is quite low as compared to that of later. Most absorption spectroscopy of organic compound is based on transition of N or pi electrons to the pi star related state. This is because the absorption peaks for these transitions fall in experimentally convenient region for the spectrum 200 nanometer. So this is also called R bands. These transitions also called R bands. So the transition bands origin due to N to pi star transition is called R bands. Such type of bands occurs wherein the molecule having acetone, acetaldehyde, octonyl, acetophenone, methylvinyl, ketone, carbaldehyde, protonaldehyde. So these are the protonaldehyde. These are the compounds examples. Protonaldehyde. This also called R bands. So the bands originate due to N to pi star transition is called R bands. So pi to pi star next. Transition in aromatic or heteroaromatic molecules also gave B band. This type of B band. Benzene shows absorption peaks at between 230 to 270. It's very nice, benzene, because it requires 200 to 700 UV. But when a chromophoric group is attached, any electron donating group to benzene attached to the benzene, that is benzene ring, the B bands observed at longer wavelength than the more intense K bands. Only more intense K bands. For example, K band appears 240 maximum, micro maximum, and this is 12,000, and B bands at 282, 286 is 244, and this is 282 micro maximum. So to 450 out of K, B and R bands. Which band is more now? This B band. So which appears in the spectrum of aromatic compounds. Out of K, B and R bands, which appear in the spectrum of aromatic compounds, R band appears at lower wavelength. For example, in the acetophenone, N2 pi star, forbidden. So appears at 319.50, while K and B bands appears at 240 and 278 respectively. The fine spectrum of B band is the case of one substitute aromatic. So this is important. What I thought now it is important. So next topic, absorption of dienes. See, first you observe this compound, absorption of diene. So this one, the energy level. This is the diene means structure. So this is actually diene, double bond. This is actually double bond, CH2, CH, CH, CH2. See 1, this is 1, this is 2, this is 3, this is 4. 1, 2, 3, 4. So 1, 2, 3. 1, 2, 3. See, in the first ground state, all are same. Plus, plus, plus. Lower, minus, minus. The second, side 2. 2 are plus, another minus, minus. This is antibond. Minus, minus, another plus. Again, you can side 3, you take 1 plus up, 1 plus below, 1 minus up, next minus below. This is side 3. This is side 3. If you take this, if you rotate this molecule, you center, if you take this, you rotate this molecule, no node, same thing is happening, will repeat. See, if you rotate this, same thing, plus is up and minus is below. And if you rotate this molecule, definitely this minus minus will come that side, means definitely is different. That's why it is. So inside to represented for there is one nodal plane. So here one nodal plane. Here, if you rotate this one, side 3, then you have this one and this one. This is one nodal plane, another thin one nodal. Rotate this one. That's why it is two nodal plane, and this is single bond. This is a one nodal band, and next one is four nodal. 1, 2, 3, 3. This is 3 nodal planes. Sorry, this is not plane, nodal plane. See, this is one nodal plane. You cut this one, equal, and this one is not equal. Plus, plus, minus, minus, not equal. That's what it is one nodal plane. If you cut this one, there is equal. Both are mirror images. That's why it is 0 nodal images. See, this is CH2, CH, 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 CH2. This is ground state.